Okay, so today we're going to wrap up our discussion of the radial distribution function, and then when we get to it on Wednesday, we'll talk about scattering theory. So we're going to be doing a little bit of jumping around today, trying to catch up on all the different individual concepts. So what we talked about on Friday last week is we went through sort of a couple of examples. We went through what liquid argon's radial distribution function looks like. We went through what liquid water's radial distribution function looks like. More often, almost exclusively, radial distribution function is given by G of R. There might be some other terms, but that is by far the most common. What it looks like is a function that has a feature that basically looks like this. It'll asymptotically approach 1. And what the radial distribution function tells us is what is the likelihood of finding a particle some separation distance. So if I have particle, let's say A, particle A prime, right, because these could be indistinguishable. They could be distinguishable as well. We have some separation distance r where the two particles are separated. So what the radial distribution function tells us is what is the likelihood of finding two particles separated by some distance r compared to what would be the regular likelihood of finding this in the bulk solution. So what we're seeing here is that you have a high likelihood of finding particles at whatever this separation distance is. I'll call it R1. Fewer likelihood at R2. More likelihood at R3, and so on and so forth. And so with the information in the radial distribution function, you can determine basically what is the structure surrounding every molecule in the system. So for the homework, you are going to need a couple of relationships. Let me go over those really quickly before we go into the details of how we actually calculate the radial distribution function. So the internal energy we can use the radial distribution function with the pair potential to determine how much energy is stored in the intermolecular structure of the fluid. So we'll have U for ideal gas. This is the internal energy that we would expect if this particle was completely isolated, it was not communicating with anything else. And we can also have the configuration energy. Or configurational energy. Configurational energy. And this tells us how much internal energy is stored in the intermolecular potentials. Right? Are they in that potential energy well for the Leonard-Jones fluid? Are they repulsed? Are they attracted? Where are we at? So the total internal energy is going to be all the energy in the velocity, vibration, rotation of the individual bonds, plus the energy stored in the configuration. Now, of course, this is assuming that the two can be isolated. But potentially in a very dense fluid, that may not be the case. Right? In a very dense fluid, how a molecule vibrates or rotates or translates may be very much dependent on its local environment. So we can use the radial distribution function, and I'll just present the equation here. And this is the exact equation, I believe, that is in the homework for question 5. Excuse me. So this first term here, U, ideal gas, if this were an ideal monatomic fluid, which is what we've been kind of focusing on for our interacting systems, that would be your 3/2 n kBt, which is essentially just the translational energy of an individual particle. Rho is the number density, the number of particles per unit volume. The U of R, this is our binary interaction, or binary pair potential. G of R is our radial distribution function. And then R squared and dr are the parameters that we're integrating across, the separation distance. So let's make sure we understand this equation, and let's go through its units. So for U internal energy, this is of course just going to be units of joules. We've already kind of looked at that and confirmed it. N is dimensionless, it's just a number. The density is some number over a volume term, so I'll just stick with SI units, that's meters cubed, 1 over meters cubed. Pair potential has units of energy. G of R is dimensionless. R squared gives us distance squared, dr gives us distance. And everything very nicely cancels out, and we get joules plus joules, because this meters cubed cancels with those two. Yes? No, n would be the number of particles, the actual number of particles. So that's one of the tricky things with going from StatMech to continuum. N is sometimes, again, the units are a bit confusing. So especially when you're working on some of these problems, you may find that your answers may differ by like 10 to the 60 or something like that. Because a couple of mistakes of the Boltzmann constant, especially if it's squared or Planck's constant, you can find yourself in very odd territory. So the units, I think, are always very important. Okay, so let's take a look at this equation here and break it down. So what the G of R is, it tells us basically what is the average number of particles separated by some particular distance compared to the bulk. So this information tells us how many particles are within some sort of a different shell. Indeed, so the radial distribution tells us how many particles, number of particles that are between R plus dr away. And this is basically a shell. So what the radial distribution function tells us is what is the average number of particles in this shell volume normalized by the average bulk density of the fluid itself. And after we go through these relationships, we'll actually go through an example of how we would calculate the radial distribution function. So the number of particles between 0 to R is given by this formula, 4 pi. Basically, what we're doing in this equation here is we're integrating from 0 to R the G of R function. As R gets bigger, you get to larger and larger and larger numbers of particles through some separation distance. So what this formula is telling us is that as we increase our R and we increase the size of our shell, this formula is counting up the number of particles within it. So we can kind of break down this formula a little bit and see that when we take the G of R and we times it by the pair potential, it's basically telling us on average how much energy do we get as we have a more strong peak in the G of R function. But that's the equation that you'll need to solve for the last problem in the homework. In addition, we have the pressure equation. If we take a quick look at this term here, this is of course just the ideal gas law. Rho, the density, is the number of particles divided by the system volume. So if we have an ideal gas, in which case this second term is equal to 0, because U of R is equal to 0 for an ideal gas, we'll just get out the equation P equals rho kBT, or which is equal to N kBT over V, which is exactly just the ideal gas law. We can go over really quickly the units again. Number divided by, well, actually number squared, which is just a number still. Meters to the 6th. We have, in this case here, joules per meter. Meters cubed, meter. Joules per meter cubed is what we end up with. A joule is a meter cubed Pascal divided by meters cubed, and we get units of pressure in terms of pascals. So units, okay on the pressure equation. The du dr, this is a force term. If you recall, the energy to sort of push an object is a force with the dot product times by the distance. Or in other words, dE dd, which is the same thing as du dr, is equal to a force term. Right, so if you're integrating a force over a distance, that tells you the total amount of energy that it took to move that object through that force field. And the last equation is the compressibility equation. And now these formula here, it's not critical that we know the derivation of them, but it's important to understand how to actually use them if you had real data of a radial distribution function, for example. Yeah, it's d rho dp in that derivative there. So the compressibility equation is an alternative to the pressure equation. because you don't actually need a pair potential to evaluate it, but you would have to redo your simulations at several different densities or pressures in order to evaluate the expression, because you'd have to integrate this expression here in order to solve for the pressure. So if you had a pair potential, you could just use the pressure equation. If you did not want to rely on the pair potential to give you the macroscopic properties, you can use the compressibility equation to give you insight into how compressible the fluid is, or you could run a number of different simulations and then integrate them. Lots of different possibilities. But the key thing here is not to be scared about seeing an equation like this and manipulating it. Right? The key thing is if you understand that the radial distribution function is just a function, you can more or less just treat these equations as dummy mathematical equations. You don't have to put any more insight into it, it's just plug and chug. But the key thing is to recognize how important the radial distribution function is to calculating macroscopic properties through intermolecular structures. Okay. Yes?
So for instance, on the pressure equation, what happens to the moles part?
There is no moles. So this is individual particles. Yeah, so if you had 10 particles, it's sort of a dimensionless parameter. So it's not moles, it's actual number of particles. So when you are applying these formula, it's for a simulation with a finite box size, with a finite number of particles in it. You say, I'm going to put in 10,000 particles into a box that's 5 by 5 by 5 nanometers. I'm going to simulate them, calculate a radial distribution function, and then use one of these equations to calculate my internal energy or my system pressure or my compressibility. So that's how we would apply these actual formula. And so what we're going to talk about right now is how do we actually simulate these particles. So I'm going to talk about two different approaches to get the radial distribution function using molecular simulations. The first one is a Monte Carlo simulation. Now, in almost all molecular simulations, we use something called periodic boundary conditions. So what that basically means is that if I were to build a simulation box, that same simulation box is effectively tiled to infinity in all dimensions. So right here I've drawn it as a two-dimensional. So if this is filled with individual particles, the same particles would be mirrored in the next box over, and here, and here, and here, and all the different other configurations. Now, the purpose behind this is to simulate a small finite volume as if it were an infinitely sized reservoir. And so long as you don't have any weird long-range interactions, we shouldn't expect that the periodic boundary conditions are going to mess things up. Your simulation box should be large enough that a particle over here only has a certain sphere of influence where you would expect there to be an appreciable effect on how that particle's position affects the behavior of all the other compounds. And so it shouldn't matter too much, right, that if you're off in some other distant corner, that it's going to matter that it's a periodic condition. Excuse me. But this is one of the most common approaches, and we call it periodic boundary conditions. Now in 3D, this is the same thing, but it'll be coming out of the screen as well. So what we're going to be talking about is the, let me just try and squeeze it on here. So the Monte Carlo simulation with the Metropolis algorithm. So Monte Carlo gets its name from basically Monte Carlo. I believe it's a famous casino in the south of France. Where's it? It's actually its own country. Anyway, Monaco, that's the one I'm looking for. right, in Monaco, which is in the south of France, which is, I guess, technically its own country, but it's surrounded by France, right? So it's basically just a casino. So the whole point of the Monte Carlo algorithm is that everything you do is random. And so what you're trying to do in a Monte Carlo simulation is to simulate all of the possible statistical spaces of the sample by randomly moving stuff around. So your first order of action in a Monte Carlo simulation, I call it step 0, is to calculate initial energy. In this case, predominantly UC, the configurational energy of the system. And we're going to call this E of n. The next step is we are going to randomly choose a particle. So for example, we could randomly say, this is the one we're going to move. The second step is you randomly change its position and orientation. So we could randomly move it to right there. That would be step 2. Now, it is definitely possible that this decision could make 2 particles superimpose, in which case we'll talk about what to do in a second there. Step 3 is you determine the new energy. In this case, we will call this E of n. And the fourth and most important step here is we calculate a probability. Okay, so this probability formula, it'll give us a number. So if En is less than En, right, which means that the new configuration has a lower energy. That move is okay. It lowers the system energy. We're marching ourselves toward minimum free energy of the system. So if 2 particles overlap, then that's not going to be the case. You're going to have an infinite energy. Now, if we have the opposite case, where the new energy is greater than the original energy of the system, we generate a random number between 0 and 1. If P is greater than R, move accepted. If P is less than R, move rejected. So if we analyze this really quickly here, if we go and look at our probability here, if En is very, very, very big, right? That means that you're having two particles overlapping. You're at some state that's an extremely high energy state. That means that your probability is going to be almost zero. So the likelihood that your random number will be smaller than that probability, right, which is necessary to have the move accepted, gets to be very, very small, unless you're at a really high temperature. So what this basically says is that we can accept higher energy moves as long as it fits into a Boltzmann sort of distribution function. And then we repeat this process billions or trillions of times until we have sampled basically every configuration of the system. And what we know from the ergodic principle is if we sampled every configuration of the system, that means it's synonymous to performing a time-based distribution of the system. Right? That's the ergodic hypothesis. Question?
For simulations, do you typically need like either a really beastly PC or like a supercomputer to run these, or at least when we're coming up with them?
So we'll actually be talking about computer power in just a moment, but no, you can do these on a laptop. It just depends on how big you want to do. So depending on your system, you may need a supercomputer, you may not need a supercomputer. Right, so the key thing, though, with the Monte Carlo, and we'll talk about molecular dynamics in just a second here, is that MC samples statistical space. It is a totally non-physical approach. But effectively, what we're doing in an MC simulation or a Monte Carlo simulation is exactly what we've been doing with pen and paper with the partition functions. We're trying to write out all the possible configurations, trying to see what can happen, scale it up, and calculate properties. An MC simulation is that same general approach, except we're not actively trying to figure out all the different configurations. We're just going to simulate the whole process and see what happens. So that's the idea behind a Monte Carlo. So the alternative is a molecular dynamics simulation. Again, we also have periodic boundary conditions. We have a system. We have particles within the system. Right, and this is repeated in all dimensions. Periodic conditions. In a molecular dynamic simulation, we have to concern ourselves with the positions and velocities of the particles. So for example, if a particle were to cross over out this side, it would reappear back on this side due to the periodic boundary conditions. So how an MC or an MD simulation works is you are solving Newton's laws of motion. So force acting on any particular particle is the mass times by the acceleration. The acceleration is given by the second derivative of the position. The force acting on the particle is from the pair potential. In this case, I'm just going to write it in one dimensional. So if we are to write out a pair potential here, like let's say the Leonard-Jones pair potential, we have U, R, I, J, separation distance between particles I and particles J, versus the plot of Rij. So we have a minimum over here. In this case, the slope is negative. The slope is positive, right? The slope is this du dr. So if we are in this region here, the force is pushing us in the positive r direction. And so the math is designed to work out with the negative sign because you have a negative slope in your pair potential, but you're pushing your particle in the positive direction. So your force is in the positive Rij direction. In the farther separation region here, right, your force is in the negative R direction, and you have a positive slope, and that's exactly what we get out of this force equation here. Right, so the negative sign is there to make everything work out. So it's pushing and pulling in the right directions. Okay. So how we actually would perform a molecular dynamics simulation. We have the mass write this out and we'll walk ourselves through it. Okay, so what I have drawn out here is the approach that we would take to solve for the new position of a particle in the x dimension. So we would have to repeat this for the x, the y, and the z as well. So let's walk ourselves through it. Actually, I'll give you a second to write it down and we can walk through it. Okay, so our goal is we want to integrate this expression here, because this tells us after some delta t time step, where will my new position of this particle be? Right? I'm solving for x. The acceleration of the particle in that direction is related to the forces acting on it, right, which is that term right there. And we're saying that we are adding up all of the attractive or repulsive interactions based on all of the pairs of all the particles. Right, so we have for every particle j, right, so for every other particle j where it is not equal to I. So basically we're summing up particle i's acceleration in the x direction. We need to add up the x component of all of the forces from all of the other particles acting on it. Now in any practical system, we typically impose a cutoff distance. So if you have a 10,000 particle simulation, we would never be able to simulate anything. Because for every single particle, you would have to calculate 10,000 forces times 3 dimensions, and then do that again for every other 10,000 particles. That's just an obscene amount of calculations. Right? And so that's why the pair potentials tend to go to 0 at large separation distance. And so at some point you say, you know what, forget about it. I'm only going to concern myself with particles that are 2 nanometers away. So the cutoff distance is a parameter that you'll control in a simulation. So the general idea, right, is that we will do this procedure for x, y, and z dimensions. You will then integrate all of these expressions So we were going to be solving for delta x of I, delta y, delta z. This basically tells us how far did my particle move after some delta t time step. And then you repeat this as many times as you want to until your system seems like it's stopped doing something interesting. Then you've reached the equilibrium state. Monte Carlo, we're sampling all the statistical spaces with no concern for reality. Particles just magically disappearing and reappearing. Molecular dynamics is trying to reproduce how the actual molecules tumble and roll and rotate around in order to give us the dynamic process. So there are some properties of a system that we can get with both MD or MC, for example, the radial distribution function, the pressure, the energy, the Gibbs free energy, the entropy, all of those can be come up with from both sides. But there are other properties that you can only get through molecular dynamics. Viscosity, right? That's a really important one that tells you how does your shear propagate through your sample. Now that's something that is most easily done on a molecular dynamic simulation, because you need to see those particles rotating and translating that shear. Okay, so now we're going to go through some calculations to tell us, okay, how long does this actually take to solve on a computer? So, a typical delta T for a molecular dynamic simulation is going to be about 0.01 to 0.1 picoseconds. So let's just say 0.01 times 10 to the minus 12 seconds, which is equal to about 10 to the minus 14 seconds. So we are very limited in how much time we can do. Right? One time step in a molecular simulation is 10 to the minus 14 seconds. So for each delta T, we need to calculate the force 3 times. Right? X, Y, and Z. We need to integrate 3 times. And this is for every particle, of course. And then we need to translate 3 times. And as it works out in the computer, this is about 100 calculations that need to be performed. So on the order of about 100 calculations. Right? Because in a computer, evaluating one formula is not like one simple crunching of the numbers. Right? Adding 2 things together might be one, what they call a floating point operation. But timesing things together could be multiple calculations involved. So the number of particles, n, is approximately going to be equal to somewhere between 1,000 to maybe 1,000,000 particles. Your simulation time, and depending on what you're working with, it varies. You know, you might be able to get away with shorter simulations, maybe you need a longer one. But I'm going to say a 10 nanosecond simulation is pretty reasonable. Which is 10 times 10 to the minus 9. So I'm going to say the number of steps, number of time steps that we have to iterate is somewhere between 10 to the 5 to 10 to the 6 steps. Right, and this is based on our time step of 0.01 picoseconds to 0.1 picoseconds. Right, so if I need to simulate 10 nanoseconds of molecules tumbling around, I need to do about 1,000,000 time steps. And this could be potentially for 1,000,000 particles. So for this simulation that I've outlined here, the number of calculations that are necessary is going to be about 10 to the 3 to 10 to the 6 particles, about, right, somewhere between 1,000 to 1,000,000 particles in your simulation, times by 10 to the 2, right, which is 100 calculations per particle per time step, times by 10 to the 5 to 10 to the 6 time steps. And that gives us on order of somewhere between 10 to the 10 and 10 to the 14 calculations. Okay, so this is our requirement side. So next, I'm going to talk about what are some computers that exist in the world and how many calculations they can perform. Okay, so somewhere between, 10 to the 10 is 10 billion to, I think 10 to the 14 is what, 100 trillion calculations? And this is just for one simulation with, 1,000 to 1,000,000 particles. So the key thing to keep in mind is that you'll never just do one simulation. You'll probably have to do hundreds or thousands of simulations in order to get a research project put together, right? Because they're not going to work, you're going to have your parameters wrong, you need to change your box size, change the number of particles. Exactly the same thing that you would do with an experiment in the lab, you have to do on the computer. So in my mind, and this is just my terminology, I don't know if anyone else shares this one, I differentiate between simulations and modeling. So in modeling, you have a definite equation that you can trust and rely on. And you may be modeling some of the parameters or modeling some of the approximations, but you've got an equation that you're holding on to. For simulation, I view simulation as an experiment that you do on the computer. You don't necessarily know what's going to happen. The calculations are so complex that you have to do the calculations in many different ways and times to make sure that you're getting reasonable results. So my terminology, modeling is, let's say, solving Navier-Stokes equation. Simulation is something like this, where you have to actually just keep on doing it to see what's going to happen. So that's at least my terminology internally. Okay, so computers are judged based on what they call flops. Has anyone heard this term before? Other than when I mentioned it just a few seconds ago. But it's called floating point operations per second. FL, floating point operations per second. Now, I'm sorry I did not look it up this morning to see what the current world record is, but from last year when I did look it up, the world record fastest computer in the world, and this is as of 2016, which may not be accurate anymore, is in China. Sun Wei Taihu Light. It is in, I don't know if I'll pronounce this right, Wuxi, China? Did I get that? Okay, good. It can do 93 petaflops, which is equal to 93 times 10 to the 15 flops. So it can handle our pathetic 10 nanosecond, 1 million particle simulation without too much of a hassle.
Standard processors should be able to handle that, like you get a rate, like a modern one, like 7 gigahertz.
Yes, so a consumer level, to compare, so a standard consumer level, what you guys may each have at your home or in your office right now, at a reasonable cost, you can get about 10 teraflops, which is 10 to the 12 flops. Now, the numbers that I had put together are a bit of an underestimate, so they're a best case scenario. So for some simulations, yeah, you can crunch them out in a couple of seconds or a couple of minutes on a desktop computer system. But let's say, for example, let's take a look at longer simulations. So for what we had talked about for what's the numbers here? So standard simulation, which is what we talked about on the last page, it'll take about 1 second on a supercomputer. Now, I'm glossing over a lot of details here. Because when you're talking about supercomputers, the only way they can get up to this high of calculations is by putting a lot of processors in parallel, and there's sort of a penalty for parallelizing your simulation. So you don't scale one-to-one. If I double the number of processors, I don't cut my time in half. Right? So we're skipping over a lot of detail. But let's say, just to order of magnitude analysis, the standard simulation that we put together, 1 million particles, 10 nanoseconds, pretty simple molecules, right? Let's say it takes about a second to run. If we wanted to do so this is 10 nanoseconds. So if we want to do a 1 microsecond, right, 10 to the minus 6 seconds, this would take about an hour. One hour on a supercomputer. And this is the entire supercomputer crunching your 1 microsecond simulation. Right? These things cost hundreds of millions, if not billions of dollars. The odds of you getting the entire computer to yourself for your simulation is vanishingly small unless you've got a really stellar idea or you've got some national security interest or something like that. Right? But you have to apply for time on these computers. You have to say, my simulations are very important. You should give me time on this computer. So Oak Ridge National Lab used to be the current most powerful supercomputer until the China one came online. And you can still, at any point, all of you, if you wanted to, write to Oak Ridge, go through their proposal process and say, I need simulation time. And that's exactly what the people in the INSCC do. Right? Phil Smith, James Sutherland, they apply and they get hundreds of millions of hours on these supercomputers. And if we scale this up to a 1 second simulation, it would take 32 years on a supercomputer. So we can only look in on the molecular world through a narrow lens. We don't have the capabilities to actually simulate the real world on a supercomputer. Right? We can only simulate small snapshots. So nanosecond simulations, we could all do nanosecond simulations. They're not that bad. You might want to get a computer with a couple of heavy-duty processors or a couple of GPU units. Not too bad. If your entire thesis was just nanosecond simulations, you might be able to get away with it on a computer, but you'll still probably want to go away and use a server cluster, like the CHCP that they have on campus. Microsecond simulations, those are a big deal. For example, there was a science paper a couple years ago showing microsecond simulations of gas hydrate formation. Right, so microsecond simulations can be a pretty big deal. There's been not much else beyond microseconds. Right, they're starting to become more and more common as computers get more powerful, but really, nanoseconds are what you're limited to in the molecular world. And with this information, then we can calculate a radial distribution function. Unfortunately, we ran out of time talking about how we actually calculate the radial distribution function. But for what you guys have to be concerned about for the homework, it's already provided for you. You don't have to calculate it from positions. But just know that we can calculate the radial distribution function if we know the positions of all of the atoms at some simulation snapshot. And in reality, how we actually calculate it is we will take a series of snapshots and then calculate the radial distribution function for maybe 100 different time stamped, like locations, and then average them all together. So that's a way that you can take your simulation of 1,000 particles and make it seem like 100 million particles or 200 million particles. Because if you run either your Monte Carlo simulation for long enough time, right, effectively you're taking a small subset and making it seem like an infinite subset. Or take your molecular dynamics simulation and run it for that one for an excessively long time. Because you're still sampling all the different configurations. So then the idea, basically, would be that if you've got your single, let's say, molecular dynamics simulation with a series of position vectors, what the ergodic principle tells us is that if we let this simulation elapse to some other delta t, that's exactly the same thing as having another simulation box with that new time steps positions. And it's exactly the same thing as stacking another one here with slightly different positions, which is exactly the same thing as stacking another box with different positions. So the idea behind the ergodic principle is if you take a small snapshot or a small simulation window and run it out for a very long time, and you have a large number of consistent positions that are all at the same general equilibrium state, you're effectively simulating an infinitely sized reservoir. So if you want to figure out how a glass of water behaves, you can simulate 1,000 water molecules for a very long time, and then you've effectively calculated the properties of a real macroscopically sized system. Right, so these individual snapshots, right, I can call this 1, 2, 3, 4. These could be going forward in time, as in the case with a molecular dynamics simulation, or in sampling space as a Monte Carlo simulation. So when you run these things out for a very long time, you get a series of snapshots. And what the ergodic hypothesis tells us is that these series of snapshots are exactly equivalent as if you had a big simulation box themselves. So you can simulate a long system for a period of time. Okay. Any questions? So now you have all of the math and theory and content to finish the homework. The only thing we didn't get to was actually number crunching. If we have a position vector, R, which is a series of position vectors R1, R2, R3, right? So one big, magical, multi-dimensional position vector tells us R1, R2, R3, R4, R5, R6. With that information alone, you can calculate the radial distribution function. Right? All we need to know is what are the positions of all the particles at some snapshot, and then we can calculate a radial distribution function. Your statistics are going to be terrible, which means you have to calculate your radial distribution function for a large number of snapshots. What an experiment does to measure the radial distribution function, a scattering experiment, it effectively does that all at once. Right? It takes all of the different configurations of the system because you have a macroscopic sized sample that you're shooting your radiation at. So I'll try my best to wrap all this up on Wednesday. Okay. Any last minute questions? Yes?
So does that work sort of in the same way that X-ray crystallography works, except you are doing it for like one sample at one time and you just put it back together?
It is exactly how crystallography works. So with crystallography, though, typically the radial distribution function isn't something that's very commonly calculated because it's once you figure out the crystal pattern and structure, that's really the most important parameter. And so you can do that just from the diffraction pattern with crystallography typically. When it comes to more amorphous or complex systems, we don't have a good way to characterize fluid structure of water versus benzene versus toluene, right? And so when it comes to a crystal structure, oh, it's FCC-HCP with this structure and this symmetry, right? They've got a whole classification system. And so for crystallographers in material science, they'll just go straight from the crystallographic pattern straight to its symmetry, blah, 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 because there's a finite number of crystal structures that have been discovered. When it comes to more amorphous and complex systems, like with fluids and soft systems, then we typically will always go from the diffraction pattern to the radial distribution function because there's no good classification system for that. But it is exactly the same theory. The diffraction pattern, all you need to do is take the Fourier transform of the diffraction pattern, and that's the radial distribution function. It's as simple as that. But the math is a bit more complex. Good question. All right. Have a good week.